What's more important is my last three slides, which is dealing with intermolecular forces. That's the new stuff for today. So, quick reminder on intramolecular forces, that would be within one atom, or within, I'm sorry, not one atom, one molecule. However, metallic and ionic are typically not referred to as molecules. Metallic bonding, remember the delocalized electrons. Again, today when we do solid structures, we're going to go over that again. But how that plays a role in its characteristics. Like metals can be hammered into a thin sheet. They can be shaped. They have very high melting points. They can conduct electricity and heat very well. This is all due to those electrons that are kind of floating throughout that you saw on the test as well. Ionic, recall that it's a metal and a non-metal held together by opposite charges. Again, it's not going to be as much of a point of emphasis now, but remember we could compare different ionic compounds to see which one has higher melting points. Ionic compounds in general, though, do not conduct electricity unless they are in a liquid form, which means you melt them down because now you can't allow a flow of current because the particles are already flowing. You could dissolve them in water and then they could conduct electricity as well. But those are the only ways that those could be conductors. They're brittle. Remember, you rub them between your fingers, they all fall apart because of that structure. But again, hopefully this slide is just review of what we went over last unit. What we're going to do a little bit more of today with that packet at the end of the hour is compare metallic versus ionic, again, based upon their properties. But then we can also compare covalent solids, and we can compare what's called molecular solids, which would be the last option here. And again, the covalent two types are polar covalent and non-polar covalent. And again, I don't think you need to write down those definitions. I'm referring to just the bond. So a polar covalent bond is an unequal sharing of electrons due to something having a greater electronegativity than another thing. Remember that you can have polar covalent bonds, but it could be a non-polar covalent molecule because that idea of symmetry. One of the things I don't mention on this note page here is, those free electrons in the central atom play a high role in electron density. Because a polar molecule has one region of high electron density, one region of low electron density. This is referring more to the bonds themselves, similar to nonpolar covalent, my second bullet point here, which is an equal sharing of electrons. And this causes the atoms to have similar electronegativity, so they don't have a one region high versus low. So, first two slides, hopefully just a reminder of the bond types. Because if we don't know the bond types, we aren't going to be able to go over these intermolecular forces. And that's the goal for today, is my last three slides coming up here of what are these different types of intermolecular forces. Once we get done with this, you picked up a sheet on the way that's going to get you practice with this to see which one would be a higher melting point or boiling point, what can dissolve in this or that. These are the types of questions we want you to become familiar with. So, an intermolecular force is a force between two molecules, which means we're going to focus on these with covalent things. And my second reminder on this slide is the intramolecular force determines the intermolecular force. Which is why we had to go over bonding in the last unit, so now we can go over this. My next slide, I'm going to start to go over some of these intermolecular forces. And then what I'm going to do is I'm going to flip over to the Smart Notebook and draw them out in Lewis structures for you as well. It's kind of common to draw that out, so we want you to be aware of that as well. Okay? Now, the term van der Waals forces can sometimes be used interchangeably with intermolecular forces. There is a slight difference between the two. I don't even use the term. Our textbook sometimes does, though. So van der Waals forces are usually referring to specific types of intermolecular forces. This one should be reviewed from Chem Life. And again, when I draw it out, maybe that'll help out. But a dipole-dipole intermolecular force is between two polar molecules. Recall, to have a dipole means you have one region of high electron density versus the other. A specific type of dipole-dipole that's a little extra strong is hydrogen bonding. Again, I will, after I get through this slide of here are three of the intermolecular forces, I'll draw each of them out for you. Now, an intermolecular force that you were not taught in Chem 1 is dipole-induced dipole. This is going to be between a polar molecule and a nonpolar molecule. Or if it's a large enough molecule, between a polar part and a nonpolar part. Because when we say dipole, that means, hey, it is polar. It has that dipole moment. But to induce something, we need to force it to happen. It's a little disgusting, but to induce vomiting if you swallowed something that you shouldn't have means you're forcing the patient to throw up. Well, the polar molecule is going to force the nonpolar thing to have a slight dipole. And the last one that we're going to talk about, and I'm going to start drawing out here in a minute, are dispersion forces. Or sometimes they're called London dispersion forces. Or sometimes they're called London forces. This one is review as well from Chem 1. And this is between typically nonpolars. However, everything actually has dispersion forces. It's just that they are a lot weaker than what your dipole-dipole would be, or your hydrogen bonding, or even your dipole-induced dipole. So these 3 bullet points are kind of in ranking of strength, if you will. Now, my first subpoint after dispersion forces is something that's commonly tested on. We can compare 2 different nonpolar molecules and see which one is held together better. When you are a larger nonpolar molecule, you have more electrons. And these electrons will create what's called temporary dipoles. And again, when I draw that out, maybe that'll make a little bit more sense to you. But the bigger they are, the more temporary dipoles they have, therefore they're held together better. Small nonpolars, not held together very well. So again, what I'm going to do is draw out an example of each right now. Let's start with HCl. This is a polar covalent molecule. The reason I know that is that chlorine is more electronegative than hydrogen. So it has a partial negative. Hydrogen end is a partial positive. When you have a molecule that has dipoles, it's like magnets now. It can stick to another one that has those types of charges. So if we compare 2 HCl's, there would be this attraction between the positive pole of one and the negative pole of another. Now, just like we could compare 2 nonpolar things, we could compare 2 polar things. The bigger the difference in electronegativity between the 2 bonded atoms, the bigger the dipoles. So even though it's a partial, it could be more of a partial for some things than others. For example, if I compared this to HBr, bromine is less electronegative than chlorine. It's further down in the periodic table. And because that's the case, bromine would be a smaller partial negative, partial positive with the hydrogen, which means it wouldn't be able to attract as well with a neighboring molecule. So again, this is what we would call a dipole-dipole interaction. So this was the first point that I had in there. Ready to move on to hydrogen bonding? So again, I'll even label this is dipole-dipole. The best example for hydrogen bonding is water. If I draw two water molecules, not only does water have a big difference in electronegativity between the hydrogen and oxygen, it also has pairs of electrons in the central atom. That really makes it a stronger dipole-dipole. When I was looking at WebAssign tonight, it asks you to check the box for which of these applies. If it's hydrogen bonding, it is a form of dipole-dipole. So typically, if you're checking hydrogen bonding, you're also checking dipole-dipole. Now, there are only 3 types of bonds that have this ability to be the extra strong version of dipole-dipole. The HO bond is one. The HF bond is another. Fluorine, after all, is the most electronegative element on the periodic table, so it definitely has a strong pull. And the third is the HN bond. Granted, nitrogen isn't as electronegative as some things. However, it does have a pair of electrons on its central atom as well. That gives that more of a oomph, if you will. So what you would want to be able to do is recognize these 3 types of bonds between hydrogen and those 3 elements. And then know that that's an extra strong version of a dipole-dipole, which then we classify as hydrogen bonding, which in covalent molecules, that is the strongest intermolecular force. So hopefully those 2 are reminders from Chem 1. So we remember all that stuff from a year and a half ago in Chem 1, right, seniors? Oh, yeah. Okay. Our last 2, both in some way, shape, or form, involve nonpolar covalent molecules. Carbon dioxide is nonpolar covalent because it's symmetrical. There is no partial positive versus partial negative end. And I'm actually going to start off with London dispersion forces here, and then I'll go backwards to the dipole-induced dipole, because this one should hopefully be somewhat review for you as well. When we draw the Lewis dot structure for something, when we draw those dots are not stationary. Those are electrons that are constantly orbiting around nuclei. At any given moment, this pair of electrons could rotate down. And if that were to occur at that split second, we would create a very tiny partial positive. And what if at that exact same moment, these electrons in the top one rotated down? It would create a very tiny partial negative. That now means we have opposite poles. Opposites attract. That would be a London dispersion force, as I wrote as LDF on there. The problem with London dispersion forces is they are temporary dipoles. Unlike with polar covalent, that is a permanent dipole, this is temporary, which means it'll go away. However, if your molecule is bigger, not only by number of atoms, but the size of atoms. Think of it as you go down the periodic table, elements get bigger. If your molecule is bigger, there are more electrons all around that can create these temporary dipoles. And if that's the case, it's a greater chance to hold it together. So on the note sheet that I had prior, larger nonpolars are going to have more temporary dipoles, so they're more likely to be held together than smaller ones. H2, not very easy to hold that together as a solid or a liquid. Almost always a gas. But there are some nonpolars that are solid at room temperature because they are big molecules. Because they are big molecules, they can have a lot of temporary dipoles. In Chem 1, I like to use the analogy of a dipole-dipole or hydrogen bond is like a rope holding two people together. It can hold them together pretty well. London dispersion forces are like threads. It's hard to hold a thread between your two fingers and someone else does the same and hold you together. But if you have enough threads holding you together, you can make a rope still. And it can hold you together pretty well. So now we've covered, dipole-dipole, hydrogen bonding, and London dispersion forces. Those are the three that we hit upon in Chem 1. Now let's move into the dipole-induced dipole. And I'm going to go back to carbon dioxide here. And water. I'll draw water a couple ways here. The name dipole-induced dipole needs you to recognize polar dipole, induced dipole is nonpolar. In Chem 1, we told you, for the most part, that polar and nonpolar don't mix. And that is more or less true. However, they do mix to a tiny amount. After all, carbon dioxide dissolved in water gives us carbonation, which is what I'm going to be drinking when I'm done talking here when I crack open that Mountain Dew. Without that, my life would not be the same, ladies and gentlemen. Let alone the fact, without this right here, we would not have something called ocean acidification due to too much carbon dioxide in the atmosphere being dissolved in water. So this must happen. It just isn't great, so it can't do it a lot. If I draw in the partial symbols, remember water is definitely polar. Let's look at the bottom water here. Its partial negative is right next to carbon dioxide. And it's right next to these two electrons. If water, a polar molecule with its partial negative end right here, is next to these electrons, are these electrons attracted or repelled by the partial negative end of water? Repelled, right? Negative electrons, partial negative. It's going to force them away. It's going to induce, it's going to force it to not be there. And when those move away, just like I showed you in the previous page with London dispersion, we've now created a slight partial positive. So now we have a force of attraction. Exact opposite here, that electrons can be attracted more towards the partial positive end to create that force there. I don't know if it's true in your life or not, but perhaps there's someone in your life that when you are around that individual, you are a better version of yourself because a little bit of them rubs off on you. Or if you ever had your parents say, oh, I don't know if I like that person as your friend, they're not a good influence, but that person, that's a good influence on you. That's basically what this is. Water is influencing the nonpolar thing to make it, hey, be a little bit like me. Come on, just a little bit. Be a little bit polar. Just because you're around me, be better. And that's what's happening here. Again, this attraction, because it does have one full dipole, is typically considered stronger than just the temporary dipoles between two nonpolars, because this will at least stay. Now again, this could be between two different molecules like I've drawn here. If we have a large enough molecule, it could be within one of the same and another one of them. But we're not going to get to big molecules quite yet. Now, technically there is one other intermolecular force that's not referenced as a van der Waals force. It's called an ion dipole force. So I'm going to draw this one out as well to wrap up our notes. But again, if we start paying attention to the wording, ion dipole. Dipole is a polar thing. An ion comes from an ion, something with a full charge instead of a partial charge. Now, once again, you can see this in a couple different ways. There are large molecules that have full charges on them somewhere, especially when you get into some organic molecules. Carbon chains with like an N that's a +1 charge here or there. That is a fairly common thing. I am going to use an example of dissolving to better describe ion dipole. And we're going to go over drawing dissolving again when we are in that part of this unit. But in Chem 1, we talked about this ion dipole attraction. If I take NaCl, full positive, full negative, but if you add salt to water, water molecules surround the Na and pull it away from the Cl. And then the Cl gets surrounded and pulled away. And recall how that would occur is, here's my Na plus, I would have waters completely surrounded, which usually it's like 6 of them, but I'm not going to draw 6, I'll draw 3. It's surrounding in that the oxygen's partial negative is attracted to the Na plus. Just like in Cl minus then, it'd be the hydrogens on water. That'd be attracted to the Cl minus. Because this is between a full charge and a partial charge, it is a strong attraction. What I would want you to get out of our notes here today is a few things. First off, kind of a ranking of which charges and attractions are greater than others. Because as you're going to see in the practice sheet here in a minute, when you have greater attraction, it takes more energy to pull them apart. This is sounding a little bit like half the questions I went over on the test just a little while ago. So with that, recognize full charges and partial charges are better than your temporary charges like you'd have in a London dispersion force scenario. Technically, London dispersion forces happen with everything, even this up here. Because if anything has electrons that move around, you could create temporary dipoles. However, if you have a rope holding two things together, adding a couple threads doesn't make much of a difference. And I bring up that specific point because you're going to see it on WebAssign today. If you see a polar molecule, yeah, you can recognize dipole-dipole, and maybe even beyond that, it's hydrogen bonding. But everything has London dispersion forces, these temporary things that also occur. So thinking about that ranking system and how the name of the force helps imply what is involved in that attraction, that's what I'm hoping that you can get out of this. So